So texture or microstructure, it is referred to as shape, size, and mutual relationship of grain to grain. It is small scale feature. So it is same as igneous rock. The grain to grain relationship and the pattern that it shows is called texture, or in metamorphic rock it is called metamorphic texture. The structure, it pertains to the large scale features such as layering. It can be layering, it can be folding, it can be alignment of minerals that result from metamorphic processes. The different patterns they will show, and then we will study those patterns, and that are called metamorphic textures. So how do metamorphic textures and structures form? So one is say recrystallization. Recrystallization means due to alteration of the pressure and temperature at a certain rock, the minerals gets recrystallized. That means they change their um, uh, mineral to mineral relationships. Okay, so change the shape and size of mineral grains without altering their identity. So they will not alter the identity. Sometimes they will form a different polymorph. Okay, recrystallization is just the old mineral will be still be intact there, but it will change its form. Okay, change its form, that will be associated with the then pnt that has been changed. So example is limestone to marble, okay, where small calcite grains transform into large, tightly packed crystals. Okay, so remember, limestone is a sedimentary rock, and marble is a metamorphic rock. Then second is phase change, to transfer one mineral into another with the same composition but different crystal structure. So here the crystal structure will be different. Example, quartz to coesite, same formula SiO2 but different crystal structure. Okay, so the phase change can happen. Then metamorphic reaction can happen, that is new crystallization. So new minerals can form also. So recrystallization is there in the first part. In the third part, neocrystallization, that means new crystallization will also happen by chemical reaction that digest the protolith mineral and form new ones. So atoms diffuse and dissolve and reprecipitate during this process. Okay, so in some parts it will be dissolved by the fluid or the metamorphic metasomatism or by hydrothermal activity. They will carry those elements and may deposit somewhere else and form new minerals. Okay, so this is called actually solution and dissolution, where some minerals erode or decays and give elements into the solution. This solution gets transported to a different area, and then it will precipitate there, forming new minerals. Then there is pressure solution, where wet rock is squeezed, causing mineral ions to migrate through water and precipitate elsewhere. Results in mineral become shorter in one direction, elongated in another. So I'll just show you how this actually forms. Say, say we have two grains. One is this, another is this, lying on top of each other. Say we have stress here. So what will happen? They will start to get compressed, right? They will start to get compressed, and they will form grains like this, where they will be hedging here. This is called pressure solution. It is called pressure solution. And this is called actually pressure solution seam. This is called pressure solution seam. What will happen? This, it will release elements, and it will, there will be solutions of AH2O, where this will release elements. So these elements then again be precipitated here. So compression is going on here, and new minerals will be precipitated here. So what will happen is it will look elongated. Okay, it will look elongated where new minerals are precipitated. These are the new minerals that are precipitated, and also this will form a elongated shape. So if all grains make like this, so this will form foliations like this. So because of this pressure solution seams, we get foliations in rock. And this happens due to solution and dissolution of rock. Solution plus dissolution, on also precipitation. So from here we'll have solution where elements will be disintegrated and will mix with the liquid or HH2O. Then this will again be reprecipitated here in the adjacent side, or maybe of different minerals adjacent side, and then it will form this elongated minerals that will be preferred in one direction. We prefer in one direction. This generally happens due to compression. Always remember the pressure solution seams or the foliations that are forming are always perpendicular to the compression direction. So this is pressure solutions. And then there is plastic deformation where minerals deform plastically without breaking. That means there will be no brittle nature. Plastically means it will be molded into different shapes under high pressure and temperature, changing shape by squeezing or shearing. This can occur alongside metamorphic reactions. Okay. So mostly these are found in ductile shear zones where the stress will be high and the strain will be high, and the um, rocks will act as a plastic manner. Okay. For example, like folds happen in plastic setting where a rock can be bent without having a fracture, without getting broken, and can be bent to form folded layers. But dissimilar to this is fault, which is actually of brittle nature, where a rock fractures and then form a plane of discontinuity, and then it slide past each other. Okay. So we will talk about foliated and non-foliated metamorphic structures. Okay, so metamorphic structures, foliation and non-foliated structures. The foliations are actually planar fabric. So foliated texture refers to the layered appearance of metamorphic rocks. Here you can see the layered appearance. This results because of foliation, and these are actually planes of weaknesses. These are actually planes of weaknesses, and which are often are due to alignment of minerals like mica or chloride. So because of this alignment of different minerals at a separate in a particular direction results in forming this planar fabric or planar weaknesses, which are called foliations. So characteristics are parallel alignment in sheet silicates. Okay, so parallel alignment in sheet silicates, preferred orientations of perpendicular to stress. Remember this perpendicular to stress, formed under differential stress. Okay, forms on differential stress. Differential stress means this. In structural geology also I will teach you what differential stress is, but here just for introduction I will tell you. So this is a box, and say we are getting stress here, say sigma, and here we are getting stress here, say sigma 2, where say sigma 1 is greater than sigma 2. So what will happen? Slowly this box will look like this, because sigma 1 is more than sigma 2, right? So that sigma 1 minus sigma 2 is actually called the differential stress. Okay, this is actually stress. Okay, stress 1, stress 2, sigma 1, sigma 2 equally is equal to sigma differential or differential stress. Okay, this is differential stress. So because of this differential stress, that means the stress amount is different in different direction, that result in this foliation. Now formed under differential stress, classified on basis of composition, grain size, and foliation type, and dominance of sheet silicates. So sheet silicates, which are actually sheet like mica, biotite, all these minerals are actually sheet like. Okay, so this will form these major foliations. So it will form slate textures, phyllites, cystose, gneiss, okay, granulite, and migmatite. Migmatite also it will form. Now non-foliated means haphazard arrangement of grains, not in a particular direction. So non-foliated texture in rocks layers, layered structure, and typically results in lack the layered structure, and typically result from recrystallization or metamorphism without mineral alignment. So no mineral will be aligned. Here you can see non-foliated rock where no minerals alignment will be there, no layering will form. Okay. So preferred orientation and foliation differentiated on the basis of the mineral assemblage. No preferred orientation. formed under no differential stress. There will be no differential stress there. Dominance of equant minerals and absence of platy minerals. Okay, so mostly these non-foliated metamorphic rocks are formed near a say a batholith. Okay, maybe due to contact metamorphism, you will find this non-foliated metamorphic rocks in contact metamorphism, whereas in regional metamorphism or in differential stress, you will find foliated rocks, or due to overburden pressure also you will find foliated rocks. The dominant of equant minerals will be there, like quartz, feldspar, garnet. These are actually equant minerals. Okay, so this will form a granulitic texture and will form these non-foliated rocks. An absence of platy minerals. Okay, so quartzite, marble, hornfels, okay, amphibolite, metaconglomerate. All these are non-foliated rocks. Then comes foliated structure and metamorphic rocks in detail. Foliation is a planar structure caused by the parallel alignment of sheet silicate mineral due to differential stress during metamorphism. Foliation forms during regional metamorphism, where rocks are subjected to directed pressure, differential stress, and high temperature over large area, typically during mountain building process or orogeny. Fine. Under this condition, platy or elongate minerals recrystallize and align perpendicular to the direction of the maximum stress or pressure or stress, and this alignment creates a planar fabric in the rock known as foliation. Here you can see this is the foliation. So remember, foliation can be parallel to the bedding planes. Also, it cannot be parallel to the bedding planes, or can be at an angle. Say we have a bedding or layered rock, sedimentary rock. Say this is sedimentary rock, and it gets stress, differential stress like this, like this. Okay, and it will form the alignment of the beddings. Alignment of the bedding will be same as that of the cystosity. Okay, as that of the cystosity, and the alignment of the bedding will be same. Now, say where where say we have a similar bedding like this, but now the stress is coming from here. So what will happen? We'll have rock like this, but the cystosity will be like this at an angle to the bedding plane. At an angle to the bedding plane, right? This can also happen. Always remember, the cystosity that will form will always be perpendicular to the differential stress. So, um, types of foliation. Now we will talk about types of foliation. So slaty cleavage, a pervasive parallel foliation or fine-grained platy minerals like chlorite formed at low-grade metamorphism. So slates are mostly formed in low-grade metamorphism that you know already. It develops perpendicular to the maximum stress due to the preferred orientation of sheets, silicates, causing rocks like slate and phyllite. Certain phyllite are more or less the same, but phyllite has a shine, whereas slate has a blackish texture. Phyllite is easily split in along the cleavage planes. So it will split along the cleavage planes. Here you can see the slaty cleavages. Original bedding was like this, horizontal. But because of this stress, you will find cystosity developing here and cleavages will form. Okay. So here you will find cleavages because of this low grade metamorphism. We call it cleavages. Okay, plane of weakness. We call it cleavages, but in later we will call it cystosity. So in low grade metamorphism, we'll call it static cleavage or S1, and the preferred orientation of sheet silicate will be perpendicular to the stress direction, maximum stress direction sigma 1. Now let's come to phyllite. Phyllite is again a fine grained mica-rich metamorphic rock formed at a low to medium grade metamorphism. Recrystallization of clay minerals into tiny micas, biotite muscovite, gives it a shiny luster. It represents a transitional stage between slate and cyst. Okay, it will represent a transitional stage between slate and cyst. Now, cyst or cystosity. It comes from the word cystosity, a medium to high grade metamorphosis rock with enlarged mineral grains and strong planar fabric. So here, the planar fabric will not be well defined because of this small grain nature of the rock. But here, because of this coarse grain nature of the rock, you can see the different platy minerals like mica and then biotite. All these minerals will be well oriented, and it will form a well developed foliation, well developed um, plane of weakness or planar laminations that will be sheet silicates, biotite, and muscovite aligned to form. So, with enlarged mineral grains and strong planar foliation will be there, and they will allow it to form cystosity, while quartz and feldspar typically show no preferred orientation. So, how this will look like? This will look like this. Here, the cystosity, which are formed by planar minerals, whereas the non-planar minerals will remain here. Okay, so quartz and feldspar will remain here, whereas the preferred orientation of seed silicates will be like this. Okay, so alteration of this will be there because quartz and feldspars are mostly rounded grains. Okay, so they are rounded grains, they are very resistant grains, and they won't form, they won't be aligned in like this preferred orientation. Whereas biotite and um, biotite, chlorite, or muscovite, mica, all those are actually are aligned in preferred directions. Then comes gneiss or gneissic banding, characterized by alternating schistose and granoblastic bands formed at high metamorphic grades. So here, gneiss, we will have alteration of schistose and granoblastic bands. So there will be bands or strong like this. It will form in schistose rock. There will be some planar features of well-oriented grains, but in gneissic rock, you will have strong bands. Strong bands mean like this, a single band where there will be all preferred orientation of grains will be there, say biotite rich or biotite rich or mica rich. Mostly this will be dark in color, whereas another rock will be, another layer will be there which is of quartz rich, feldspar rich. This will be another band which will be lighter in color, lighter in color. Okay, these are uh, not well oriented. These are planar fabric. Again, another band will be there like this. So alternating bands of planar fabrics and non-foliated, non-aligned grains. Here you can see dark colored grains are aligned, mostly of biotite. Okay, and then light colored grains will be like this. So pyroxenes can also be there, having aligned like this. Okay. So characterized by alternating cystose and granoblastic bands formed at high metamorphic grades. As sheet silicates becomes unstable, dark minerals like hornblende and pyroxene grow and segregate into distinct layers, producing gneissic banding. So dark layers will be mostly of biotite, muscovite, pyroxene, amphibole, whereas these non-foliated layers will be of rich in quartz and feldspar. Okay, then comes granulite, a high-grade anhydrous metamorphic rock, anhydrous, okay, because it is formed very high pressure and temperature, containing orthopyroxene and granopyroxene and plagioclase and quartz. At peak metamorphic conditions, seed silicates break down, resulting in coarse grain phonetic texture with little to no preferred orientation as seen in Dhava granulite and Charnocite. So these are actually very old metamorphic terrains of granulite where we do not get to see preferred orientation, and mostly we will find as this coarse grained granulotic texture because of high amount of recrystallization. Then we have metamorphism, metamorphic differentiation and causes. So formation of compositional layering, gneisses and cyst due to differential stress during metamorphism is called metamorphic differentiation. The formation of this differential layering is called as actually metamorphic differentiation. Now causes and processes. So preservation of original bedding plane. So some compositional layers may reflect original sedimentary bedding. So here you can see this is sandstone, these are the beddings. But here sigma 1 is like this and the cystosity is like this. Okay. So here in this we can track the original bedding as well as the cystosity, which is very good for us because we now know that the original layers were actually deposited like this, but after a event of stress we got cystosity like this, right? This is mica cyst and this is quartzite. So foliation may cut across the bedding due to the recrystallization under differential stress. So as why it will cut? It will cut because the mica cyst, or sorry, the cystosity has formed after the deposition of the beds. Because here you can see shale and sandstone were deposited first, then the foliation took place because of this stress sigma 1, and the cystosity will cross cut the bedding plane because it has formed later, right? So, in highly deformed rocks, folding and shearing can stretch and obscure bedding. So, in say in highly deformed rock which has faced multiple amount of stress from different direction, multiple episodes of stress. So, in that way, we can identify the bedding planes. Here you can see there were bedding planes here like this. Then stress came up and formed like this. So people may often do a error in saying that the beds were originally aligned like this, but it was not actually. The beds were horizontal only, but because of this pollution and pollution happening because of this stress resulted in rocks which has lost its original planar beddings. Okay, so it makes it hard to identify when it has formed episodes or high amount of deformation was introduced in the rock. Then transposition of bedding. So under compressional stress, new foliation develops an angle or to original bedding. Bedding is broken into pods, which realign with foliation due to recrystallization and deformation. This forms new compositional bands parallel to the new foliation. So here you can see the original bed was like this, then it got folded because of the ductile nature of the rock. Remember, in brittle areas where the rocks are susceptible to being broken or susceptible to breakage, they won't form folds. Areas which are where rocks are in ductile nature, mostly at uh, greater depths, we get ductile nature of surrounding, and then we get folded layers there. So here you can see first we got folded, then the alignment of different micas and quartz resulted in formation of this vertical type of orientation of the different layers, and finally it was like this. So most people who's observing a rock at this stage we can make an error of saying that the beds are like this, but actually the beds were horizontal only, but because of this folding and this segregation of micas and quartz, it resulted in forming beddings like this. Okay, so transposition of bedding can take place by this folding activity. Then solution and reprecipitation. Here you can see the stress causes minerals like quartz, feldspar to dissolve by pressure solutions. Pressure solutions where solutions come and then take away some parts of the mineral or elements from it and then reprecipitate elsewhere at fold hinges. Okay, reprecipitate elsewhere at fold hinges where pressure is lower. Okay, resulting in alternating bands of mica rich and quartz feldspar rich. And so here you can see the pressure, and then it is forming at fold hinges. This is the fold hinge, and then it will form layers like this. Then preferred nucleation. Metamorphic fluids dissolve minerals and transport ions. Felsic minerals preferentially nucleate elsewhere, forming discontinuous felsmafic bands. So it can happen because of this nature of deposition. Felsic minerals predominate nuclear elsewhere. Okay, so felsic minerals are always nuclears at different place, forming discontinuous felsic mafic bands. So because when a solution comes, it will take different elements into account, say Mg also, Fe also, then silica also, aluminium also. But felsic and mafic have different tendency to precipitate at different locations depending on the pt condition. So that is why reason there will be segregation of felsic and mafic minerals, and it will form layers and bands. Then at last comes migmatization. In high grade conditions, partial melting produces felsic melts. These migrate and recrystallize into pods or layers, migmatites. Deformation may stretch, fold these bands beyond recognition. So migmatites are actually metamorphic rock only, but here partial melting can take place. Deformation may stretch or fold these bands beyond recognition. This is how cystosity is connected with the bedding planes, and the major learning that we get from here is that while while a geologist do a field work, he or she should note that there can be occurrence of a cystose layers apart from the original bedding plane, and he or she should identify those layers and then reconnect the history beyond that, with how that has formed, where the stress direction where, and should not often make error taking the cystosity as the bedding plane. Okay, this error should be avoided, and because a lot of times cystosity is often taken as bedding planes, or often identified mistakenly identified as bedding planes. Okay, so this was about foliations in rock. This will be the end of this class, and next class we will talk about non-foliated structures and metamorphic rocks in detail.